Again, yeah, welcome everyone. My name's Stuart Finn. Just a quick introduction before we get into today's webinar, which looks like it's full of a lot of exciting content. I do want to acknowledge the traditional owners of the lands on which we're meeting across the country, past and present, and their emerging future generations and future leaders. So just before we start, we did want to say a few words on what's happening with our Advancing Earth Observation 2020 Forum. At the moment, we're progressing with planning for that for the end of September 2020. We are still obviously taking advice from the Queensland Government along with the various institutions which are helping us deliver this exercise. If we do need to postpone or change it, it will be within within 10 or 12 months of the original date. So at the moment, it's still proceeding as normal, and we're extremely excited that we do have a lot of sponsors on board already. Geoscience Australia have come on board as the founding sponsor for the forum. We also have a number of state and Commonwealth government agencies, universities, local companies, and large multinational companies who've also committed to funding the event and participating. Please keep an eye on our website and our email list, and we'll let you know how things are changing over time with that. So before I hand over to Agnes Lane from the Bureau of Meteorology, I would like to thank all our presenters today for getting everything ready and providing their time for this. I'd also like to thank Larissa Marfan and Joe Edkins for the setup and organisation of today. So with that, I'll now hand over to Agnes. Agnes, if you can share your screen now, please.
Thanks, Stuart. And thank you for inviting me and the Bureau of Meteorology to host this webinar. I think, I'm a little bit biased, but I think that the presentations we've got lined up for today are really exciting and interesting, and I hope the community gets something out of it. Before we start, can I just remind everyone to keep their audio muted? And if you've got questions, you can type them into the chat bar on the side, or you can save them to the end. We'll be answering questions right at the end of the three presentations. I'll try my very best to keep everyone on time. So with that, we'll start with the first presentation, which is from Chris Griffin. If I can start his presentation. Okay, can everyone see that?
Where did the comments go?
Sure.
Yes, we can.
Okay, great. All right, Chris, over to you.
Well, good morning. I'm just going to talk to you a little bit this morning. Probably many of you know or don't know that the Bureau is involved in satellite reception, and we have some products as well. And I just really want to talk a little bit about the kinds of products and things that we're doing and producing and things that we're looking at the Bureau. This is not an exhaustive presentation, but I hope it sort of gives you some idea of the breadth and the things that are available. The names under the title there, Satellite Products, Leon, Vincent, David, Pallavi and myself. Really, we're sort of a small core team in the research group at the Bureau. There are many other people in the Bureau who who have interest and overlay in doing things with satellites, but we are the guys who, if you like, are doing the applications development, making sure that the things that are running keep running, and keep producing products and looking into developing and deploying new products. And so we're a fairly small team there in the satellite application section. So I kind of wanted to break the talk down and talk a little bit about low Earth orbiting platforms and then geostationary platforms, and then talk basically, it's going to be a sort of a smorgasbord or a listing of sort of the kinds of things that we do. There'll be some pictures about with some of those things and a little bit of explanation, but mostly we're just going to, I just want to make a list and give you an idea of the breadth of what kinds of things we're looking at the Bureau. And so in low Earth orbiting platforms, you know, there's some things that we do with the AVHRR sensors on the old NOAA POSE platforms, and also MEDOP as well. And some of those things are things like solar radiation, grassland curing, and sea surface temperature. We have routine real-time generation of those products, and those, so those things are available for people. On AIRS, we've got the sounders, and we produce data from that for the GTS, but also NWP, which NWP boundary conditions, but also for our internal NWP. And John's going to talk a little bit about that in a little while. So I'm just kind of skipping through these kind of things, because the big focus for us is, and for our weather, our forecast is really in the visualization part of it in the geo world. So anyway, we'll just skip over the low Earth orbiting platforms. So some of that stuff with AVHRR is because we've been receiving direct broadcast AVHRR right the way back through CSIRO, and quite collaboration with CSIRO and AIMS and other people as well, right the way back from before 1992. We've actually got a decent archive of all that data in HRPG format right the way back to 1992. And there's also been reception stations in Antarctica too. So you can see the coverage there in the diagram. And that's the kind of direct broadcast reception, if you like, of AVHRR. So it's very, very high resolution AVHRR, and the archive has been collected and expanded in real time. It's available on NCI. And again, this is all in collaboration with CSIRO, Geoscience Australia. There are Bureau reception stations, and other people have it too. So we have that sort of archive database, if you like. And based on that, one of the things that we got some years ago, Helen Beggs and the Bureau got IMOS funding to deliver sea surface temperature from that record. And so we have, swath-based, a lot of sea surface temperature products, which are based on single sensor stuff, multiple sensor stuff, daily, interpolated, multi-swath, multi-sensor, multi-data. So there's many, many kinds of combinations of that derived from that data set. They go right the way back to 1992. So some of those things that are used downstream is there's a climatology that's been produced. I'm not sure if you're aware that we have a sea surface temperature climatology around the Australian region. It has a 1 kilometre resolution, very high resolution one. And that's the first of its kind. It was produced in 2016, 2017, and that's called STARS. It's also used in CSIRO downstream in the ocean current system, and it's also used in the Bureau for our reef temp next gen coral bleaching, now casting, and all that stuff too for the Great Barrier Reef. And so those are the products. Okay, audios keep dropping. I'm sorry, we've just got messages through here. Can you all hear me? We're just going to stop and see if we can figure out what's happening to the volume. Is that correct? Is that okay now?
Yeah, maybe just get closer.
Yeah, it's Stuart here. If you can just keep talking directly at your microphone.
Yep.
Even if you just angle your head away slightly.
Yeah, I'm just moving the screen and my head around just to try and, that's okay there, is it?
That's perfect. If they're aligned, okay. Awesome. Thank you.
All right, I'll try and keep it there.
Yep, sweet.
We've got these downstream products where people are using the data that comes out of this long-term archive, but also in real time to produce, as I said, there's climatologies and for on the Great Barrier Reef, for reef temp, and also in ocean current looks. And so that's what the pictures are really there representing. And these are all, as I said, collaborative products that come from CSIRO, and some of that is also from other groups in the Bureau. So that's the sort of LEO platforms. We do that for this Predominantly the sea is the one that's the most developed. We also have land-based product as well. And you've got the island grassland curing and some other things too over historical longish time series, but not all the way back to 1992. That's typically the late 90s. We have them back to there. And then in addition to that, the Bureau is also doing things in real time, I guess you could say, with the geostationary platforms. And predominantly those are things like the Japanese geostationary platforms, and there's some animations that were on there which don't seem to be working now. Never mind. Of the Queensland fires and Victoria fires, just to see the kind of things that we get from geostationaries. We actually have an archive of geostationary platforms right through all three generations of the Japanese geostationary satellites, going back to GMS-1. And so you can see there's quite a long sort of data holdings of those platforms right the way back from about late 1970s to Himawari 8, which is the third generation here. And we've started receiving a little bit of ComSat, but not very much. Mostly that's focused on the rapid scan thing, which I'll talk about in a minute. For those of you who haven't seen the Himawari 8 and the GeoComSat, the two geostationary satellites, I'll just put that picture up there. If you squint hard and focus in front of your face, you can see that they're both at different longitudes, and so you get a three-dimensional stereoscopic effect. And so we're sort of, a lot of people are really excited about using that information to try to add to the kinds of things that we can start to see now with these geostationary satellites. I'm not sure if you want a little bit of time just to try that. You just sort of squint and you get that 3D stereoscopic effect. So I said, it's not something that we've started playing with yet, but it's something that people are sort of holding out for a great possibility for, in terms of research, but also in terms of what maybe we can give our forecasters as well. Primarily though, the Bureau's focus is on low latency solutions, because we want to use this data in real time, and we want to use it for advice to the public, but also for forecasters as well. And so this particular diagram here shows how that actually works. And you see in the blue there, that's the Himawari 8. This is for Himawari 8, but the blue bars are the observation time, and then the yellow bars after that are our processing times. And so you can see from the diagram there that we have two types of observations from Himawari 8. There's the one in the middle there, which is labelled, which is sort of takes about 10 minutes. Every 10 minutes we get a full disk, and we're targeting the reception, and in the processing obviously needs to be less than 10 minutes after the last reception, but we're currently sitting around 4 or 5 minutes after the last reception, and that's good, because we want that to be as near real time so people can see what's happening right as it happens. We don't have any delays and latency in that. Now the rapid scan, which is the chart below that, is like a 2.5 minute or 2 minute scan of a very small region of the disk at a reasonable resolution, but that small region of the disk can be moved around with time, and so we can use that, for example, to observe things like cyclones and other kinds of strange events, fires and cyclones and things like that. And that moves around over time. And so we have some holdings and some archives of those particular rapid scans that follow cyclones and things like that over long periods of time. And again, our goal is with a 2.5 minute latency to get that information available. Himawari 8 being the Japanese one, we're also planning to do with ComSat 2 with the Korean one as well. But that's really part of the value that I think the Bureau adds to the equation, is this low latency solution, delivering the data in as close to real time as we possibly can. So that's why, our focus and support for Himawari 8 is really, and for this geostation, is really on this near real time and nowcasting activities. So you can see stuff as it happens. So you can see here, I think there's a volcano in Manam, Papua New Guinea, and when you're getting those 10-minute views in a true color image, you can see the volcano blowing off there. And literally, you would see that in real time, or 5 minutes behind real time with the processing that we have. And so that's good because we can send alerts and add value impact for the Australian public. Here's another one, Victoria from geostationary orbit, and again, seeing some fires there. There's a fire that comes up there in the middle of the screen, and you can see the smoke and it becomes pyrocumulus in the picture as well. So those are important products for us, and we produce those RGBs, just true colour, red, green, and blue, and also for the night we have infrared microphysics and other things as well. And so, you know, those are the things that are important for our forecasters, so we produce those products in real time, and we've actually measured the impact of that, and mostly it says that well, you can see from the chart there that all of our microphysics products have had large positive impact in terms of forecasters' work and being able to predict things when they happen. That's work that Bodo and Agnes and others have been involved in, and it's really good to see the results of what we're doing there. So from the geostationaries, we also do sea surface temperature. That again is IMOS funded, and that's a geostationary that allows us to, so we're getting 10 minutes hourly, 3 hourly and daily, near real time over the full disk, 2 kilometres, and that allows you to see the ocean currents actually moving and you'd be surprised how much activity there is over a 3 or 4 hour scale, but you can really start to see those diurnal effects in the motion and the currents when you're talking about hourly, 3 hourly sea surface temperatures. There is data on NCI for that, and again, CSIRO is one of our downstream users of those products. The other thing that we're really trying to move into in what we do with satellites at the Bureau is this giving advice, meteorological advice in real time. So that would be either you know, what's happening right now or what's going to happen very, very soon. And at the moment, Australia does a lot of that. It's mostly around things like severe weather and thunderstorms, things like that. And we do a lot of that with radar. But you can see from the diagram there that there's a good motivation for using satellites over Australia. And that's basically that, except for the heavily populated areas, we don't have a lot of radar compared to, say, the US or Europe. And so there's a strong motivation to provide that advice from a satellite-based product. And so one of those products that we have is this basically 3-band satellite rainfall product. Again, the emphasis for us is on producing things quickly. And so that generally means that you're using simple multi-channel fitted kind of algorithms. We do radiated transfer on some of our products, but again, it depends on the timeliness and when we can get the things out. And you can see here on the left, the animation of the satellite-based product, and on the right, there's the actual radar detection. And at least if you squint hard, it's not doing too bad a job. It's really not doing too bad a job. So we're sort of developing those things and calibrating, verifying those things to try to get a better version of this kind of real-time continental coverage that you can do with the satellite. So one of the pieces of that is getting the NWC SAF nowcasting package, and what that'll allow us to do is to do real-time cell tracking of rapidly developing thunderstorms. So that's based on, because of this severity heritage, we've got a lot of packages around in different parts of the world. So a lot of what we do is about using those packages and that research that's been done elsewhere and then applying it to HIMAWARI 8 and the Bureau's context and producing real-time advice for our forecasters. And so we're planning on doing things like, and that's actually in the process of development right now. And so we're looking at things like cloud top temperatures, lightning, derived motion vectors for the atmosphere. And that'll help us to deliver, again, that real-time advice. And so on the right side there, you can see polygons of identified storms laid over the imagery, showing where the clouds are, and you can see how that's sort of corresponded. And here's another one showing where the storms are identified on the left and cloud properties on the right, which has also been produced from the satellite data. And here again, for the verification part of that, we're looking at how do we visualize and track these storms and compare them against back against the radar over the places where the radar is, and against lightning strikes and other things that we can use to check the veracity of the forecasts that are coming out. And so in the process where our contribution comes into that NWC SAF work is really in the real-time verification, where we actually get a chance to develop metrics and tests for how consistent these short-term statuses and nowcasts are, and then maybe to enhance the processing, but also have ensemble-based predictions or a layer of post-processing that allows us to add probability advice along with the forecasts that are being made. The NWC SAF package, we think will probably give us about 30 minutes to an hour in terms of forecasts about when these severe thunderstorms might hit. A lot of collaborations that we do, obviously a team of 5 people and a lot of demands operationally. We also have to do some science sometimes to make the products work and to get them from somewhere. And so there's a lot of collaboration that goes on. Here's an example of a blended product which we're planning on doing moving forward into an operational framework. But again, that's something that's under evaluation. The general idea there is to take the radar. You can see those 3 images there, the radar, the NWP and the satellite retrievals, and then blend them in a sensible kind of way so that we can see, if you look on the chart there, you see that the radar works on very short time scales and the satellite works on sort of shortish time scales too. And then the NWP is better on the longer time scales. You can see where the frequency spectrums are. They all sort of match at large wavelength, which is where you'd expect the NWP to match up. And then it has a bit of problems in the middle there at the mid-range wavelength, whereas the satellite and the radar sort of track each other. And so we're hoping we can use the satellite to help to fill in the gaps between not just the spatial gaps that exist between the radar, but also some of those temporal spatial, where the time and space trades off in terms of the power spectrum in between, some of those in between things where the radar is starting to get less good and the NWP is maybe still struggling to give us a good picture. So we're hoping maybe it'll help us to fill in some of those gaps. So there's plenty of opportunities for collaboration, lots of things going on. So we're looking at precipitation estimation, flood understanding, water detection, against storm cell tracking, fire detection and hotspots, aerosol as well, and a little bit of aviation as well. So we sort of find ourselves at that hotbed of collaboration in between, pulled in very many directions, but then still trying to get out these products that provide impact and value. I think that's the way everyone likes to talk about it. So what have we got currently available? Well, subscriptions are available for things in NetCDF4, so you can get data in NetCDF4 from HUMARI 8, for example. You can also get imagery, which could be in JPEG or GA2 format, and that would be the RGB true color imagery, and it could also be some of those false color infrared imageries as well. And we have corrected reflectances, which are Rayleigh corrected. You can see from the left and right there, they make them look like the real color. And there's a paper there from Broomhall you might be interested in reading. GeoTIFF images for GIS services, we also provide those, and you can get those things in real time. There is a virtual lab and regional focus group that Bodo and the other people in Training Centre run, and that's really good. So I just want to highlight that there so that you can see that's something that we also involved in. And that's really about all I want to talk about. Thank you. I hope you get an idea anyway about some of the things that we do. Thank you.
Thanks, Chris. So Chris really covered the part of the Bureau that develops products for forecasters, for forecaster display. John the Marshall is going to talk more about the satellite products. There are satellite data that's assimilated into NWP. John and I had a bit of a friendly argument earlier about how many satellite data streams we actually assimilate. I thought it was around 20. John thinks it's around 40, but that's an argument for another day. So let me hand over to Professor John the Marshall. We'll cover, please save your questions for the end.
Yeah, I think the discussion was how many satellites are used to provide in NWP, and the tricky part is we use the GPS, and of course there's GPS, BEIDO, GLONASS, a whole lot of satellites you can add to the list, and it's really almost impossible to define. Okay, I'm going to talk about improving analysis and forecasting using Earth observations from space. Fortunately, Chris has gone through and talked about forecasters using visible imagery and water vapour imagery, colour enhanced images, volcanic ash products, etc. I think not Zara, but Vasily is going to talk about the space weather applications, and Chris has also covered NDVI, grassland curing, solar radiation, etc. This here is just an image showing one of the typical products from Chris's neck of the woods, in case you didn't show many of them. This is just convective rainfall rate coloured onto a cloud image as it cascades off the southeast corner of Australia. What I'm going to talk about mainly is numerical weather prediction and the data that goes into that. Typically, you have to populate, before you do a forecast, you need to populate a grid with a four-dimensional grid, in fact, with temperature, humidity, wind, and surface pressure. And to do that, we use microwave and infrared sounders on polar orbiting and earlier geo sounders. We use GPS data to do that as well, for temperature profiling, as well as determining total amount of water. And wind we determine using scatterometers, where Bragg reflection is used to give wind speed and direction at the surface, radiometers like WindSat, Doppler wind LiDAR, which has just recently been launched, Aeolus, and the old favourite atmospheric motion vectors, which sort of started in the 70s, or earlier, where you can actually track cloud elements and work out wind speed and direction. Typically, in a top quality forecast shop, 80 to 100 satellite data streams are used for a high resolution global model. I'm not going to go through and describe the satellites we use and the instruments associated with them, because that would take 30 minutes of a 20-minute talk. But basically, there are a large number, and as I said, it's almost impossible to define how many, because they go back in several layers through the products. I was going to talk about three key ones. One is the hyperspectral infrared sounders, which measure the radiance going into space in thousands of channels. And from this, they can invert the radiative transfer equation. You get temperature basically to within 1 degree RMS and moisture within 5 to 10%. The way they work basically is when you measure 1,000 channels coming up from below, each channel can more or less be associated with, a layer of the atmosphere, and gives you an estimate of the mean temperature of that layer. And by unscrambling the egg, you can get a temperature and moisture profile. These satellites are the big hitters in terms of global prediction. Second thing are the atmospheric motion vectors, which I talked about before. There you can follow clouds in a sequence of images, or you can follow the water vapour field to get speed and direction, and you can then radiometrically from the channel observations of the instrument determine the height of the wind. And the other thing I put in, because it's comparatively new, is using the GPS instrument. In fact, we use what's called radio occultation. When this satellite, the low-flying LEO, goes behind the Earth and GPS satellite sets, you can actually use the bending angles of the signal to determine a temperature profile. And at the same time, if you've got GPS receivers around your country, you can calculate the delay in the signal getting to the GPS signal and use that to determine the total amount of precipitable water. Again, here's just a list of some of the satellites and some of the instruments, and they include, as I said, AIRS, 2,378 channels, CRIS, 2,211, AMSU, which is AMSU A and B, a 20-channel microwave, and so on. ATMS up here is a 22-channel microwave, but these instruments, there's just a plethora of them, and they're basically these ones here are all used in the Bureau with others. The data from these is then fed into an analysis system and a forecast system. The key analysis systems we have are a global one, which is 11 kilometre resolution, and the little red squares you see here, which are the capital city model, which is 1.5 kilometre resolution. That's over most of the highly populated areas. And there's also a heritage regional system of 12 kilometres. How important are these data for forecasting? Well, I think this diagram summarises it all. This shows you the fall off in accuracy of a forecast with time, a global forecast when you're not using satellite data. And you can see at 24 hours, the correlation of the forecast with the verifying analysis is about 0.9. That's if you do a forecast without satellite data. When you add satellite data, you can find the forecast goes out to 4 days. So 4 times the forecast length for the same accuracy when you add satellite data. So it extends the forecast length for an accurate forecast by a factor of 4. In the Northern Hemisphere, that factor is 1.6. And you also must remember these people are paying for the satellites. So it's not just, say, talking about geopotential height as I was before. If you start talking about elements like moisture, this shows a forecast done here on the left with satellite data, a forecast without it there, and the same 48 to 72 hour forecast verification here. And you can see the actual, having the satellite data makes the forecast a lot more accurate, and in this case gives emergency services the time they need, which is about 48 hours to set up. And that's generally the problem. When you look at tropical cyclone tracks, you effectively double the forecast track error by not using satellite data. So there's just a whole lot of applications where the satellite data is the key to an accurate forecast. Which of the myriad of instruments, and it's like acronym soup here down the left-hand side, but all these are different instruments that are used operationally. The red ones are the satellite ones, and the length of the bar tells you what contribution they make to removing errors in the forecast. And you can see here the advanced sounder EASI's on top, followed by the microwave sounder, followed by atmospheric motion vectors. And they all improve the forecast, and they all make a significant contribution. But without the satellite data, we wouldn't have forecasting like we have it now. I'll just talk about a couple of new things that are going in at the Bureau at the moment, largely in already. One is use of 10-minute winds from Himawari 8 and 9, and the other thing is the use of GPS data, because it's a little new. For many years, we've put winds, home-generated winds into our system. It started in about 1990s. In fact, we were the world's first fully operational automatic system. And with the advanced sounders too, I think the first publication of the big impact of advanced sounders on operational forecast was actually published in the Australia Met-Mag. So the country's got a little bit of heritage in this. This plot just shows the impact of adding our own winds to the reduction in errors of wind speed over the Australian region. But basically at both 24-hour forecasts and 48-hour forecasts, the addition of our own winds significantly improves the wind field in the model. At the moment, we now get 10-minute data from Himawari 8. We process every 10 minutes and produce data every 10 minutes, but I think we may still be the only people doing that. And we also try and use as many channels as we can, because both the channels and the different images contribute to the number of vectors and the quality of the analysis you get. I've just got an example here of Tropical Cyclone Kwong, which actually occurred when Himawari was being installed operationally. And operationally, we didn't produce the world's best forecast, as it turned out that day, unusual. But what we did was we went and got the Himawari experimental data off the satellite when it was under test. We took that data and processed it. And you'll see here we've got Kwong starting out on the 29th of April out to the northwest of Australia. And over the next couple of days, it came ashore near Exmouth. We actually took the Himawari wind data and generated wind vectors. And this is an example here of the field. The magenta ones are the upper level ones, and this one here, which has got 4.5 feathers on this wind barb, means 45 knots. The one over here with a big one, a small feather on the barb, means we've got a 15-knot wind going that way. Well, all this data, the 2 kilometre infrared data, and at this stage we used 1 kilometre visible data, which I think is probably one of the first times we've done. This all went into the forecast, and the subsequent forecast with the new wind field actually is the red line here, which followed the best track data, which is the black dots. And what was a quite poor forecast along this yellow trajectory with the errors increasing very quickly with time was reduced significantly by just this data. Now, the plot I showed you before, where it showed the contribution of each instrument, shows that AMVs improve the forecast, and this actually shows you how big the improvement can be on particular cases. At the moment, we've just had a new satellite launched, Aeolus. This is a Doppler wind LiDAR, and it actually calculates the wind speed in the radial direction from the satellite. The reason I show this again is to make people know that if you look at the RMS errors, when you synthetically look at the impact of what this instrument will be, if you look at, say, a 2-day forecast in the Southern Hemisphere, you see adding the satellite data reduces the error in wind speed by about 25 to 30%. That's the Southern Hemisphere. When you go to the Northern Hemisphere, for the people who again pay for the satellite, you find there's very little impact. So we are both very dependent on EOS data, and at the moment we're dependent on people in other parts of the world making a contribution. I think I think that's something we should keep in the back of our mind. The last thing I'm going to talk about is the use of GPS data. Over Australia, there are hundreds of GPS sites, and these sites actually allow us to work out what the delay is of the signal coming from the GPS and other GNSS satellites, and from that we can determine the total perceivable water in the atmosphere. And these data are now being processed and collected at the Bureau, and they go into our operational global model and about to go into a high-resolution capital city model. I'm not going to go through how it works, but basically ZTD is the delay in reception of a signal from a GPS satellite, which is directly overhead as a result of the presence of the neutral atmosphere. And then once you know that delay, you can then go back and effectively compute the total perceivable water. Now, the processing we have now is the ground stations you can see on a little plot below here, and each of these stations are processed by RMIT and GA, who use slightly different algorithms, and then send them to the Bureau. So overall, we've got 256 stations across Australia, moving towards 700, and I think there are plans to put another few thousand out to help with precision positioning and also precision farming. The advantage to us is, of course, we don't pay for any of this, we just collect the data and use it. As I said, the processing is done by RMIT and also GA, who use differing methodologies. But what we've got is basically, when this is all finished, we'll have ideally a dense, redundant to some extent data set, so we should have no trouble with data into the future. Now, what I'm going to do is show you what these data do to the analysis and forecast system. These have been fed into Access C3, the capital city model, which runs at 1.5 kilometre, and the data has been used together with the full database, which is, again, 50 different satellite data streams. And if you take these data and assimilate them every 10 minutes with 4-dimensional variational assimilation, that's the technique we use right through the Bureau. And 4-dimensional variational assimilation means you actually get a 4-dimensional block of data, which has radiances, ZTD, all these other things, and you find a model state that fits all the data effectively in an RMS sense over the time period. And then once you know that model state, you then continue it forward, and that's your forecast. So it's conceptually trivial, and I'm going to show you now some results from using this. The top plot here shows a heavy rainfall event that occurred on the 1st of December 2017, and the 50 millimetre line, rainfall line, is where the cursor is moving up the screen. Now you can see this is verification data from the Bureau's AWIP system, and it shows the 50 millimetre lines just up to the northeast of Australia. If you run the Melbourne Capital City forecast model without the ZTD data, that 50 millimetre line moves out here too far to the east. And you can see by adding the GNSS data, in this case, the 50 millimetre line, which is this point here, actually moves, this point along here, this colour, the border, actually moves and goes roughly back into the right place. So you can see adding the ZTD data has influenced the heavy rainfall over Victoria in this case. And if you look at synthetic radar data, you can see that using the Melbourne radar, there's a system here to the northeast raining heavily at the time, and another rain band across Western Victoria. When you run the forecast and use the ZTD data, in this case there's a band heading towards the northeast here, and the other rain band over Western Victoria is portrayed. Without ZTD data, again, there's very little of the northeast band here, and the full band over Western Victoria isn't there. What I'm not saying, it's not like this every time, but it makes this much of a difference to a forecast. And then what you have to do is go and do statistics on this month after month. And in this case, where I've got some quantitative verification, you can see that the verification in the fraction skill score, which measures the accuracy of rainfall, you can see that the graph here, the blue one, that's used GPS data is more accurate than the one without GPS data. And this sort of verification goes on day in, day out, and I'll be able to give you a few years of the data when it's done. So in summary, the ZTD data has potential for improving moisture and rainfall analysis and forecasts, and the density of the system will increase over time at no cost to the Bureau. The last thing I was going to say was just a little bit about the future. In terms of what needs to go into space, one option for Australia is to actually build a small CubeSat radio occultation satellite. This was, I guess, recommended by the Space Research Conference to the Space Agency a couple of years ago from the conference. Fortunately, it's not expensive and it's been taken up by Newcastle University. So a satellite with this capacity is under construction at the moment, and this will hopefully allow Australia to make some contribution to EOS. And the big thing that will happen in our region is in about 2028, a geostationary advanced sounder will be flown, and it'll have a 2-kilometre footprint, the same resolution as our high-resolution models will have then, and this will significantly improve our analysis and forecasting capability. And this is clearly an area where we really would like to get local industry and an Australian contribution, because at the moment we make a small contribution, and in a day where it looks more and more likely that charging for observations is becoming more prevalent, it'd be good to be seen to be a fuller partner in EOS. And I guess my last thought for the morning is looking down is looking up.
Thank you, John. So the next presentation, unfortunately, Zahara Bouya wasn't able to make it today, but we have from our Space Weather Services side, Vasily Lobzin to give Zahara's presentation. So in addition to the weather observations, weather forecasting, we also have a Space Weather Services area based in Sydney, and they have observations of space weather parameters, and they make space weather forecasts and warnings from the Sydney office. And so I'll stop sharing my screen, and Vasily, would you like to drive from your end?
Yeah, yes. So can you hear me?
Yes, perfectly.
Okay, thank you very much. Okay, so okay, I'm going to talk mostly about satellite observations which we use in our everyday activities. A brief history of our team. Actually, originally, Ionospheric Prediction Service was created shortly after the Second World War, just to support high-frequency radio communications. Recently, in 2008, we have joined the Bureau of Meteorology, and we are operating Australian Space Forecast Center for many, many years. That is our webpage related to space current conditions in space weather. You can see several rows. The first one is related to solar observations. It shows solar wind, X-ray flux, etc., and current radio spectra. The next line shows geomagnetic conditions near the Earth and the corresponding warnings and alerts. The next line is for our high-frequency communication customers. Again, in this screen, everything is green. It means that we don't have warnings at that moment. This line shows the current ionospheric conditions. More precisely, it shows the critical frequency of the ionospheric layer. Red color means that the ionosphere is depressed and not good for radio wave propagation. Green and blue color means that everything works well. And the last line corresponds to is for our for global navigation system. It shows total electron contents. This video will get you an idea about different events which are relevant to space weather. Okay, I'll try to summarize what you saw in this video. A solar flare happened on the solar surface, and it was accompanied by coronal mass ejection, which can be considered as a huge amount of solar plasma, which is injected somewhere. And if this cloud will hit the Earth, it will cause geomagnetic storm, and a lot of particles in the near Earth environment will be accelerated. Then they can drop down to atmosphere, and you can see auroras. That's another movie which will show approximately the same thing, but maybe in more detail. So the first slide shows so-called active regions on the solar surface, which are bright. So a flare should occur in that region, and followed by CMEs and all other phenomena, which I have mentioned recently. So that's the solar flare in progress. Yeah, and now you can see a snow-like feature, which actually caused by cosmic rays generated during the solar flare when they hit the spacecraft detectors. I'll run it once again. This instrument shows the so-called CMEs, coronal mass ejections. I'll run it again to show you more detail. So these are active regions. Now you can see coronal mass ejections as clouds moving from the sun. And then energetic particles accelerated during the solar flare and by the CME hit the detectors of satellite, and we see this snow picture. Now we go back. We go to satellite observations, which we are using now to produce our forecasts. Maybe one of the most important satellites are GOES from GOES series. Unfortunately, for the moment, only one is operational. It's a new generation of GOES satellites. It can observe, it has different instruments. For our activities, we use data from these three instruments. So they are able to measure, to observe the solar disk in extreme UV, and in addition, it can measure fluxes of X-rays from the total disk, plus fluxes of energetic particles near the Earth. These are typical pictures that can be found at the American website of Space Weather Center. The left picture, sorry. The left picture shows profiles for X-ray fluxes, and you can see some sharp peaks. They correspond to huge flares of X-class. Such flares are very often accompanied by coronal mass ejections. Then the next one shows fluxes for relativistic electrons with energies 2 MeV and higher. These electrons are very important for satellites because they can cause some problems due to deep charging effects if the fluxes are high enough. And this, the last plot shows flux of energetic protons. It shows you that the flux has been elevated and exceeded a threshold of 10, which is considered as a significant event. And actually, this event should result from an X-class flare before, but I don't know with which flare it is associated. This slide shows a picture of a new instrument which was not installed on the previous GOES satellites. It gives us solar images in extreme UV at several different wavelengths. For the moment, we don't use this data, but we are using data from another satellite. However, the last one is the end-of-life satellites, and we don't know actually for how long it will work. That is the satellite which I have mentioned before. It's Solar Dynamics Observatory, SDO. It's located at L1 point between the Earth and and the sun, and it is watching the sun 24 hours a day. The data which we are using usually come from atmospheric imaging array, which is using 4 different telescopes, and give us images similar to those shown on the previous slide, like these images. Such images allow us to observe active regions on the solar surface. So these are active regions. They are so bright and look white here in such images. In addition, we can see some structures in the solar atmosphere. So that's a filament which can disconnect at some stage from the solar surface and go away into space and may hit the Earth. So this picture also shows active regions. In addition, we see some dark areas here. That's a coronal hole, which is usually accompanied by high-speed solar wind streams, which again are very important for our predictions of geomagnetic activity and behavior of the Earth's ionosphere. That's a very old satellite, which you see has been launched in the previous century, but it is still operational and very important for our observations. Usually we are using data only from one instrument from this satellite. This one. This instrument is called coronagraph. It shows us coronal mass ejections. You can see it here and in black and white picture. Oops, sorry. So actually that is the most important solar phenomenon for space weather at the Earth. We need to know in which direction these clouds of solar plasma are moving, at which speed. We have to estimate the time of arrival, and in addition, it's good to know the magnetic field which is associated with this plasma cloud. However, to do this, we need more than one satellite, because we have to have 2 different points of view to get a better estimate of the speed. If we have only one point of view, we can measure the so-called plane of sky component of its velocity. It does not allow us to get any reasonable accuracy. Fortunately, there is another mission which is actually basically scientific. It's called STEREO. Several years ago in 2006, from the Earth, 2 satellites were launched. They were called STEREO A and B, which means ahead and behind. So their orbits are similar to that of the Earth, but one of them is slightly closer to the Earth, and the distance from the Earth for another satellite is slightly bigger. That is why they are moving around the sun with slightly different speed. And actually, well, okay. And when they are far away from the Earth, they allow to observe the sun from different point of views. Unfortunately for the moment, so that's a relatively recent position of the satellites. The satellite ahead is now approaching the Earth. The satellite B goes away from the Earth, but unfortunately B is not operational at all. And the satellite A is, I would say, is half dead at the moment. It does not provide measurements of the solar wind speed, etc. but it still measures the solar wind magnetic field and takes images of the sun as well. So it's still useful to detect CMEs, coronal mass ejections. This satellite was launched to measure the solar parameters of the solar wind not far from the Earth at so-called Lagrange point L1, which is very close to the Earth actually. And it measures both the composition, but for our predictions, we need, first of all, plasma velocity, plasma temperature, density, and magnetic field embedded in the solar wind speed. Again, that's a very old satellite, but it is still operational. In 2016, it was supposed to be replaced by a new satellite, which is called Deep Space Climate Observatory, or DSCOVR. However, from my point of view, it does not work very well for the moment, but we don't have anything better at this stage. This slide shows a typical picture of the solar wind data which are measured either by ACE or DSCOVR satellites. And they show, the top panel shows magnetic field profile. Black line shows the total magnetic field, while the red line shows the so-called BZ component, which is essential for geomagnetic activity. If we have a negative BZ for a long time and it is big enough, plus the solar wind speed is not small, then we will get a geomagnetic storm. And this picture shows two CMEs which hit the Earth in the past. They're associated with X-class flares, as far as I remember, and they show the CMEs as observed from DSCOVR or ACE satellite in terms of magnetic field, density, and speed and temperature of the solar wind plasma. Here you can see an increase in the magnetic field. It is accompanied by a jump in the solar wind speed. We can also see a jump in density, but not always. And here we see a very long period of very negative BZ. And as far as I remember, one of such CMEs was accompanied by very strong geomagnetic storms. Actually, coronal mass ejections produce the strongest geomagnetic storms. In addition to satellite data, we are using ground-based data as well. We have a network of different instruments. We have, so historically, IPS had a network of INOSOND across all Australian region plus Antarctica. And in addition, we have some measurements for total electron content. We have magnetometers, which ours plus Geoscience Australia. And as far as I remember, we also have Japanese magnetometers as well in Australia. Another important instrument is radiospectrograph. We have, for the moment, one operational, which is located in Le Mans and jointly operated by Bureau of Meteorology and US Air Force. It shows it is important to have such measurements because it provides additional information about coronal mass ejections. So it's possible if you don't have optical data and this happens, we may have an opportunity to estimate the speed of the coronal mass ejections using data from this instrument. That is all. Thank you for your attention.
Many thanks, Vasily, and also for stepping in at very short notice. That's a really interesting presentation.
Yeah, unfortunately, Zara was sick, and she has asked me to replace her. And yeah, so
Yes, can you please,
I'm not
Vasily?
very well prepared for this presentation.
No,
I have to
I
say
thought that was fantastic. I thought that was a fantastic presentation. If you could just stay on the line, because we'll go to questions now from the audience. So if anyone has any questions for our three speakers, I might start with the questions that came up through the chat, the online chat. One of them was on ocean colour. We do have an ocean colour product for the Great Barrier Reef area, but I'm not sure that we have a national product. I know that there's a collaboration between the Bureau and CSIRO. There might be someone online that can answer that one better than I can. Is there anyone that can answer the ocean colour question?
Sorry, I can't answer this question.
There was another question from the community on the availability of the Bureau's satellite data in general. It has been difficult to access the Bureau's data. We recognise that. We make the Himawari data available on NCI. And then once it's old data, it goes into our tape archive and it's never seen again. We are looking into providing a better service regarding our archived data. That's a year or two away. It's probably easier for us to provide relatively real-time data to the community. And if you do have that request, let me know. Let me know what data you want for either for operations or for research, and we can look at making that available. Were there any other questions on data availability?
Yeah, hi Agnes, it's Mark.
Hi Mark.
I was talking to Vincent a while ago about getting access to something like Panther, which I'd quite like.
Chris, can you answer?
It's kind of, yeah, there's so many things about Panther that are sort of internal, I suppose you could say. So I think that's just something that we need to have a broader conversation here about what actually would need to be done to host that externally. But yeah, I can't really add anything to that at the moment.
Yeah, we don't. It's Panther's for those that aren't aware, is a visualization tool that we developed in-house for our forecasters. It displays satellite data, but it also displays in situ observations, model data, forecasts and warnings.
And also flags when they're not correct.
Yeah. I'll take that question on board, Mark.
Got some nice animations there, by the way.
Thanks. There's some, yeah, there's mostly Vincent's, I think.
Yours wasn't bad, Mark.
Yeah. No worries. Thanks, guys.
Oh, Mark Broomhall. Hello.
Yeah. Thanks, Mark.
This is animation, I showed.
The other question that came up on the chat was regarding NDVI. We used to produce an NDVI product, but it had there were some issues with the satellite, and then there was which resulted in quality issues in the product. So we've turned it off for now. We're working on making this available again, but unfortunately we don't have an NDVI product at the moment. Are there any other questions on NDVI? Nope. There was another question on bushfire products. So the Bureau produces products for our forecasters, in particular fire hotspot products and some smoke products. We make these available to emergency management services and agencies. I'm not sure if we make them available to the broader community. As part, you may have heard of the initiative at the moment, the Australian Space Agency is developing a roadmap for, in response to the recent bushfires. And the roadmap includes what we can do between now and the next bushfire season and what we might do in the longer term. And as part of what we can do now, one of the things we will be doing nationally at the federal government, state government, research and academia level is cataloguing all the satellite product, all the bushfire products that are available. So that's something that should be available before the next bushfire season. Were there any further questions on bushfires? No. Just scanning through the questions. I've got a question for Vasily. Vasily, if you're still online, you showed an event of coronal mass ejection from September 2017. What was the impact on the ground, or was there any impact observed in electricity power networks, on satellites? GPS, are you aware?
Do you hear me?
Yes.
Yeah, so for this particular event, I cannot say anything because I don't have the corresponding information. However, I can give you just a general answer. So actually, geomagnetic storms are the most maybe important space weather effects at the Earth because they have very many consequences. First of all, just geomagnetic storm. Varying magnetic field means that induction currents are generated in long pipes or long power lines or whatever. And if the currents are really strong, transformers can burn or whatever, and you have to take some precautions to avoid these problems. And we are doing some research on this, but I'm not in that team. I cannot say more detail about this. Another consequences related to high frequency radio wave propagation, because usually after storm, during a storm, you may see an atmospheric enhancement. However, ionosphere becomes more turbulent and we have some degraded propagation conditions. But shortly after the storm, it could be depressed and significantly depressed, and you may not be able to use high frequency communications at all. The worst case.
Okay,
so these are probably the most important consequences.
thank you. Thanks, Vasily.
Thank you.
I don't see any more questions. Stuart? I should actually say that the presentations will be made available on the EOA website.
Sorry, Agnes, I'm back on
Yep.
now.
Okay.
Yeah, you're right. So this has been recorded and it will be available on the website within the day. Just to answer some of those other questions, there's a whole webinar on the status of basically fire prediction, active fire mapping and fire burn extent and intensity mapping from December if people want to look through it. And likewise, this will be a unique new resource for today. So really, thank the BOM team for putting all of those things together as well. So Agnes, if you want to stop sharing your screen, I'm happy to just to go back on. So I did have one question though, Agnes, while you're all online, which is, I mean, the Met Bureau has a lot of research needs it looks at internally, but it would be helpful, if we can figure out a way for Met Bureau to engage or let other people know how they could engage with key topics. Increasingly looking at research grants, CRC grants, they need to be focused on solving problems, and I see a lot of wasted activity for people proposing, research which isn't really going anywhere at all and just testing algorithms. It would be really good to keep our community focused on addressing needs, particularly of our, critical infrastructure like the Met Bureau. Have you got any thoughts about how we can make those connections better?
I think that's a, shall I put the video on?
Sure.
Okay, here we are.
Okay.
There's John, Chris.
Hey everyone.
Yeah, no, I think that's something that I've thought about a lot in the past. Mentioned we have a really small satellite applications capability in the Bureau. It's only a team of 5. We should be sharing our research priorities with the broader community so that we can solve problems collaboratively. I don't know how to do that. Suggestions?
Yeah, that's why I asked the question. I think partly it is a bit of a new challenge, and maybe to allude to another activity is the Space Agency will be releasing a roadmap on its national civil priorities. Earth observation is one of them, and so a number of us like yourselves are involved with that. Maybe that's a way that we can use it as a mechanism to say, let's, Earth observation, research, education, and that does need to be directed to strengthening and building, our essential capacity in this area, like in meteorology. So that might be one way to start. There could be other ways that we could do it informally through, prioritising research topics through EOA as well. So, yeah.
Yep. Did you have a suggestion, Chris?
No, I was just thinking there's sort of some reviews and internal stuff going on that focus the satellite group, and I guess that's part of that is going to be in identifying needs and making collaborations, maybe more efficiently or more purposefully. So we're doing some personal navel gazing and we're doing some organisational navel gazing as well. So I think there's some good things coming out of it. Yeah, it just takes time. So.
Right. Thanks, Chris. I mean, if those things can line up, I think doing that also helps the community understand that you operate within mechanisms of government and have certain constraints. We've got certain things as well, but I think the research community is really being pushed to make sure what you're doing is being used to support critical things. So I think there's a good way of joining things up there. So let's keep that dialogue going.
The other guy is, if you're interested actually in contacting that and doing that, Leon actually takes the brunt of that stuff at the moment. So he's not conference, but he's the contact who sort of really has his head over everything that's going on in that with us. Yeah. So if people who are listening and maybe want to start that conversation, he'd be the place to start.
Okay. Yeah. I'll follow up with Leon and Agnes afterwards about how do we do this so there's not just tons of email.
Got a comment here from John.
Oh, sorry. John.
Yeah, no, I was going to say one of the things that I think we haven't done effectively yet is the fact that we have people around Australia, for instance, using Himawari data. And the Bureau, for instance, has been using Himawari since 1976. So things like navigation, calibration, a lot of the things that people need to do and need to understand and often want to refine, a lot of that has already been addressed in the Bureau, recalculating orbital parameters and so on. So one of the things I think we should do is make sure that the people who are, say, working with Himawari applications or some polar orbiting applications in pretty much the same area get to know each other so they don't reinvent the wheel in different parts of Australia, which I think is happening to an extent now. And probably a good example is both, for bushfires, you really want really good navigation in terms of where the fire is and so on. And for generating cloud-drift winds, you have to have sub-pixel accuracy or the wind speeds are no good. So there's lots of things that it mightn't be apparent to people generally, but there is a lot of common problems across the whole area. And I think making an effort to have people share the knowledge would be very beneficial to everyone.
Right. I mean, I think that's something we could look at within Earth Observation Australia for online discussions. It may also be something that we could look at with a bit more intent for the AMOS, the Atmospheric and Meteorological Oceanographic Society meetings, the annual Space Research Conference, and then the forum that we're having as well. So if we know there's, once we move through the current situation, we do have these events where people are meeting. We could have those, but then have online discussions as well. So, I mean, today's talks were excellent, I think, in really opening it up. I think a number of us have seen what's there already, but the more widely known what's out there and the extent to which we're critically dependent on these resources and people who know how to use them, it'll help us move forward. So, cool. No, it was excellent. Thanks, Agnes. Did you want to say anything else before we sort of get to the end of things?
No, I just wanted to thank our presenters.
Yes, very much so.
Great. Perhaps one thing, just to answer your previous question, perhaps one thing we can do is share the recently released R&D plan
Okay.
with the community. We'll find out if that's possible.
Yes. Yeah, if there's a publicly suitable one, we're happy to distribute that, and also help us focus research resources towards that.
Yep. Okay.
So with that, if there's no other questions, I really do want to thank Agnes, Chris, John and Vasily for the presentations today. That was excellent. It's going to be a really useful resource moving forward. Please keep an eye on our website and our sort of LinkedIn and Twitter feed as well. We'll update you as things change, the forum and other things as well. So thanks everybody for your time today, and then thanks also again to Larissa and Joe and the team.